Here we're going to look at question 6 from section 2 of the ENGAA 2018 paper. In this question, we're given the following diagram of a stationary wave in an open-ended tube. We're told that the tube has a length of 0.5 meters and that the wave in this medium has a speed of 1000 meters per second. Next, we're given a diagram of the wave just in a medium by itself without the tube at all. So it's going to have the same speed and it's going to be the same in every other way. Then the question asks us, what is going to be the value of time at our position x shown on the diagram? If you'd like to have a go at solving this question yourself, then please pause the video now, otherwise we're going to have a go at doing it. So the first thing to do with this question is probably to wonder why they're showing you a diagram of a stationary wave. Well, the reason for this is probably so that we can try and work out the wavelength of our wave. Now, we're told that we have the tube of length 0.5 meters, and we can see in this tube that we have half of a wave, and it goes from the minimum right up to the maximum here, which is going to be half the wave. So that means that the total wavelength of our wave is just going to be double our 0.5 meters, so the wavelength will be 1 meter. There's nothing else really which we can tell from our diagram, so it must be that this is the only information which they're trying to tell us here. But why is this useful? We now have a wave speed and a wavelength. Well, this might make you think of the equation that c is equal to f lambda, with c being the wave speed, f being the frequency of our wave, and lambda being our wavelength. So, with our wave speed and our wavelength, we can rearrange our equation to get the frequency of our wave. So it's just going to be our 1000 meters per second divided by our 1 meter. So our frequency is going to be 1000 hertz. Okay, but why is this frequency useful? Well, let's think about what frequency actually means. So a frequency of 1000 hertz means that in 1 second, we have 1000 cycles of our wave passing through a set point. Now what this means is that one oscillation of our wave is going to take 1/1000th of a second. So I've written that here as 1 times 10 to the minus 3 seconds. Right, so now that we know this, let's go ahead and look at the final graph we're actually asked about. Now we can see that in this graph, we have one whole oscillation of the wave plus another half. So we're looking for the time after 1.5 oscillations of our wave. Now we've just found out that one oscillation takes 1/1000th of a second. So that means that 1.5 oscillations of our wave is going to take 1.5 times 10 to the minus 3 seconds. So we can then see that this answer is going to correspond with answer F given the question.